This is Katie Bowman's AP problem number 13. We'll start with part A. In the boxes provided, draw the complete Lewis structure for each of the three molecules represented below. So the first one is CF4. So I started by writing the element and then how many electrons it still needs to complete the octet rule. So carbon needs 4, and fluorine, there's 4 fluorines, they each need 1. When you add that all up, you have 8 electrons you're looking to get. You divide that by 2, and that means we're going to need 4 bonds for this one. So since C needs the most, you're going to put it in the middle. It's going to be your central atom, and then you're going to have the 4 bonds going out with all of your F's. They're all going to be single bonds. And then you have the electrons, the lone pairs on the outside of the F because it has 3 lone pairs on each of the elements. So the next one is PF5, and this one's different than this one, and we'll see why in a minute. So I started out by doing the same thing. I wrote the element and then how many electrons, valence electrons it still needed. So P needs 3, and then there's 5 F's and they all need 1, so that's 8, and you divide that by 2 and it's 4 bonds. But for this one, since P is in a d orbital, it can break the octet rule and go above 8 valence electrons. So instead of just having 4 bonds, we're going to have 5 to have all 5 fluorines in there. So you add the 5 bonds, you have all the fluorines on the outside, and then you draw the lone pairs all the way around. And then we have SF4. So S needs 2 more valence electrons, and 4 F's each need 1. So that's 6 divided by 2, and that's 3. But again, the S is in the d orbital, so it can break the octet rule. And so S is in the middle because it needs the most, and then you add the 4 F's all the way around, and S has 1 lone pair because it has 6 valence electrons. So we have 1, 2, 3, 4, and then 5, 6 are right here. So yeah. And then part B, on the basis of the Lewis structures drawn above, answer the following questions about the particular molecule indicated. So part 1 asks, what is the FCF bond angle of CF4? So this is the CF4 molecule, and it's 109.5 because it's a tetrahedral geometric shape. It's 4 bonds and no lone pairs on the central atom, so that makes it tetrahedral. Part 2 asks, what is the hybridization of the valence orbitals of P and PF5? And that is DP3, or DSP3. And then part 3 asks, what is the geometric shape formed by the atoms in SF4? So this is the SF4, it has the lone pair. So that makes it a seesaw because it has 4 bonds and 1 lone pair. So you see the 4 bonds with the fluorine and then the 1 lone pair because it already has 6 valence electrons. And then the last part, part C, 2 Lewis structures can be drawn for the OPF3 molecule as shown below. So we have 2 structures, and the only difference is the P has a double bond, or the O and P have a double bond in structure 1, and then this one does not. So part 1, how many sigma bonds and how many pi bonds are in structure 1? So we see that it has a double bond, and a double bond consists of 1 sigma and 1 pi bond. So we know that we have 1 sigma and 1 pi, and then we have 3 single bonds all the way around. So that's 1, 2, 3 more, 3 more sigma bonds. So we have 4 sigma bonds and 1 pi bond. And then part 2 asks, which of the 2 structures are best represents a molecule of OPF3. Justify your answer in terms of formal charge. Structure 1 would be the best because they all have a formal charge of 0. So like how many valence electrons it already has minus how many bonds it has on the molecule, and all of them, when you do that, adds up to 0. So yeah.